Hi, I'm Arnav Adak, and welcome to our Calc BC project, the work of drinking through a straw. So, introduction of experiment. So, in this experiment, we're trying to answer the question of how much work does it take to drink a glass of water through a straw? Given the concept of work, we can determine the time required for this action. To quantify the work, we can figure out how long it takes to drink. This measurement takes power. What is power? It's work over time, or the derivative of work with respect to time. Power in US customer units is measured in foot-pounds per second. By measuring the rate of power it takes when drinking, an estimate we will find through a separate experimental measurement later, we can determine how much time it takes to drink, given the work needed in the cup straw system. We can then compare that to the experimental time found.
So before we start the experiment, we're gonna go over some quick notes really quickly. So first, we're gonna assume that the force being applied to the straw glass system is constant. And so we're saying as the water is being drunk, that the amount of force being applied is the same the entire time. Second, we're also gonna assume that our power estimate is a constant that allows us to find the time to drink algebraically. It'll be the work calculations that are actually calculus based. Third, if the power is constant, then power equals work over time, and thus the work divided by the power will give us the time required to drink the water. And then some analysis of the experiment. At first glance, this experiment might seem like a simple work problem. However, we want to quantify the work done with a measurement by finding the time it takes to drink, and not just the theoretical amount of work it would take to suck all of the water out of the glass. To do this, we had to figure out the amount of work that could be done per second. By finding the average amount of work applied when drinking from a straw, we were able to use this value along with the total amount of work to more accurately predict how much time it would take to drink all of the water.
The experiment. First, in order to predict the final time it takes to drink, we need an experimental measurement for power to make predictions about the time. To do so, we found how long it took to drink the full volume of a straw of a diameter of 1/8 inch across and a length of 9 3/4 inches above the water. It took approximately 0.08 seconds, and it was achieved by drinking until water filled the straw. Then I was the one who measured this. I basically put my tongue against the top of the straw to create a vacuum so that I could then accurately measure how much time it took to drink just the volume of the straw and not any more water in the cup. And then the calculations for this, we treat this as a simple work problem of a cylinder. So this has a diameter of 1/8 inch and a length of 9.75 inches. However, we will need to convert these to feet to give us the required unit of foot-pounds. Now work is force times distance, and the force, because this is US customary units, it's weight times volume and not mass times gravity times volume, because gravity is already accounted for in the weight in US units. And water is about 62.5 pounds per cubed foot. Now to find the volume, you have to think of these as little disks with a height of dy, or a little infinite thickness and infinitesimal thickness, and a radius that is constant because the sides of the cylinder are straight. The radius is going to be half the diameter, or 1/16 of an inch, but converting that to feet, it is 1/192nd foot, pretty small. And then pi, of course, because these disks are basically little circles with a thickness. The distance is going to be how long each disk has to go up to the top. So it starts with, at the top, basically a distance of 0. Then as it grows, the y value basically shrinks. So basically, it is 9.75 inches over 12 to find the feet minus y. We then put this work into this equation. These are constants that can be put out in front. And then this integral is saying all the little disks of water and how much work it takes to bring them up, because this is the distance with that dy thickness. We get a value of 0.00176 foot-pounds of work, and then power is work over time. It took, measuring this, about 0.08 seconds, giving a power estimate of 0.0212 foot-pounds per second. With that and the dimensions of the cup and straw system, we can estimate Daniel's drinking time, for it was Daniel who actually did the experiment of drinking the whole cup of water. And the experiment itself was just Daniel timing how quickly he could drink a cup of water. Note that with these dimensions, we assume that the top 3 inches that point above the cup just act as the spout of a pump, giving height but not a new cylinder with little discs that needs to be measured. It'll just be the discs of inside the cup with a diameter of 3 inches and height of 6 inches.
So here we have some photos. On the left, we have the cup that we used, which was 3 inches of diameter and a 6-inch height. And then we have the metal straw that we used to calculate the power when being applied when drinking the water. And then on the right, there's a photo of me actually doing the experiment, and the total time it took to drink this was about 35 seconds.
So, yes, so the cup problem is basically the same process that was with the straw. However, the little extra bit is that these 3 inches of straw are like the spout of a pump that give extra height, but not an extra cylinder. So the volume is still the same process. The radius is half the diameter, and then converted into feet, it's about 3/24 feet. The distance, however, is slightly different um, because it will be the entire height of the straw plus cup, which is 9 inches or 3/4 foot, minus the y distance between the discs and the top of the straw. And the work here is the same, but then notice that the integral is only from 0 to 1/2, which is the 6 inches, again converting into feet, because the discs only go from the top of the cup, from the bottom to the top of the cup, and not the straw itself, but the straw gives extra height, which is why these two numbers are different, unlike the straw power. Now, finding this, now we could find this with the reverse power rule, but then we'd also have plenty of constants. So finding this, it becomes 0.767 foot-pounds of work is the estimated amount of time, or not the amount of time, the estimated amount of work. Then, using a power output of 0.0212 foot-pounds per second, the foot-pounds cancel out, giving us an estimation for seconds of 34.90 seconds.
Okay, so now finally for our results. It took Daniel a total of 34.72 seconds to drink the glass full of water. Our prediction was 34.9 seconds. Using the percent error formula, our percent error was 0.518%. It is interesting to note how treating the straw as a spout for the cup straw system did not alter the expected value in a large way. This also gives a more concrete and observable example of the physics concept of work.
Thank you for listening to our
Thank you.
presentation.
Thank you.